All right, in this video, I want to talk about how to estimate the error variance, which is sigma squared. Okay, and in the previous video, we came up with these two equations for calculating the variance of our estimators B0 and B1, right? And, we can calculate, we can figure out what n is. We know n is the sample size. X bar is the mean of the x's. This guy, we can figure out what he is because it's the sum of the differences from the mean of x squared. So we can figure out this guy, and we can calculate this variance of B0. However, we're missing a piece, right? The piece that we don't know how to we can't quite estimate the variance of B0 because we do not know what is sigma, right? Sigma squared is not something that we can just calculate and know based off of our sample. So instead, what we're going to have to do is we're going to have to estimate sigma squared, right? So just as a reminder, what is sigma squared, right? Let me write this down over here. Sigma squared is the variance of the model error, right? So remember, our model is yi equals beta naught plus beta 1 xi plus epsilon sub I. So the variance of epsilon sub I is by definition what sigma squared is, right? And if I were to take the variance of y, this is exactly the same thing as the variance of epsilon. So this is the same thing as saying the variance of y, right? So sigma is the variance of y. Okay, and so if I want to estimate the variance of y, back in the old days, let's imagine I only have data on y. So all I have is y1, y2, y3, etc. Okay, if all I had was data on y, I would use our old estimator, s squared equals the sum of the differences from the mean. So xi minus y bar squared divided by n minus 1. Okay, so this is back in the old days when all I had was data on y, or on one variable. I would use this estimator for the variance. Okay, and so it's the sum of the differences from the observation to the mean, right? And you square those differences, so square differences between the observation and the mean, divided by n minus 1. Okay, so recall, why are we dividing by n minus 1? So basically, I'm trying to find the average distance from the mean, right? That's what my estimate for variance is. It's the average distance from the mean. But why is it that I divided by n minus 1? Okay, if you remember, we have calculated and figured out in the past that the expected value of s squared is sigma. That is why we have that n minus 1, so that it is a unbiased estimator. So the expected value of s squared is sigma squared. Okay? Alright, so that's in the past. Right? But now, we don't just have data on one variable. We have two variables, and we are assuming that this model is correct. That's a very important assumption right now. We are assuming that this model is correct. All right, assuming that this model is correct, my unbiased estimator for sigma is different now. Okay, so it is going to be s squared equals the sum. Okay, we're still going to take the difference between our observed y, but instead of subtracting y bar, now we're going to subtract off the estimate of the y, so y hat, the predicted value of y. Okay, and we're still going to square it, so we're finding the difference of all of those between the observed and the predicted, right? Divided by n minus 2. So now it's n minus 2 instead of n minus 1. Right? So why is that? Why is it n minus 2? Well, I mean, it basically comes down to the same rationale. This s, the expected value of s squared, is sigma squared under the assumption that this model is correct. Okay? As long as this model is correct, then this is an unbiased estimator. And that's why we have n minus 2 on the denominator, to keep it unbiased. All right, this n minus 2 is often referred to as the degrees of freedom. Degrees of freedom. Right? And, or DF. And in general, the degrees of freedom is the number of observations. So this is going to be the number of observations, which is n, minus the number of parameters estimated. Parameters estimated. Right? And remember, right now we are estimating 2 parameters, beta naught and beta 1. Right? Before, we only were estimating 1 parameter. That's why it was minus 1. The one parameter that we didn't know before was what is mu, or the mean of y. Okay? So that's why in the past it was minus 1. Now it's minus 2 because we have 2 unknown parameters. All right. Another thing I want to mention about this formula, I'm going to write it again down here. S squared equals this sum yi minus y hat squared divided by n minus 2. All right, this difference here, yi minus yi hat, right? yi hat, remember, is the predicted value of y. So that difference is the error, right? So this is equal to the sum from I equals 1 to n of I squared divided by n minus 2, right? So a lot of times we will use this formula instead, and it's assumed we know that I equals this difference. Okay, so it's the difference between your observed value and your predicted value. Okay, and so once you see that, it becomes really clear that this term up top, the sum from I equals 1 to n of E sub I squared, this guy is called the sum of squared errors, SSE. All right, and then when we take s squared and this SSE divided by n minus 2, this is often referred to as the mean squared error. The mean squared error, MSE. All right, and these are acronyms that you're going to want to memorize. SSE and mean squared error, MSE. You're going to see these popping up a lot, especially when you're doing your data analysis in Excel. It's going to tell you SSE and it's going to tell you MSE, so now you know what those are.